All set.
Perfect. Hi, everyone. It's so nice to see you all here virtually. My name is Caitlin Mueller. I'm an associate professor here at MIT in the Department of Architecture, and I'm also currently the director of the Building Technology program, which hopefully you're here to learn more about today. This is a virtual open house for prospective graduate students interested in one of our 3 graduate programs. And the plan for our session today is to give you an overview of the details of the academic programs, highlights and interests of faculty research that you could collaborate on if you join us as a graduate student, a little bit of advice about how to apply, what we're looking for, how to tailor your application to us, and then a Q&A with us, but then also without us with current graduate students who can answer a lot of your questions. So with that, I'm very happy to get started. I'm going to share a little bit of an overview of the program before turning it over to my colleagues who will each tell you more about their own work. So I have a brief presentation here to share. In just a moment. Georgia, is it possible? Can you see my screen?
Yep. Yes,
It's working. All right, fantastic. So this is us, the Building Technology program at MIT from a few years ago. We are an interdisciplinary program between architecture, engineering, and science who are focused on technological solutions to improving the sustainability and quality of the built environment across a range of sectors. We're highly motivated by sustainability and reaching our carbon emissions targets that are urgent in the coming years in the light of the climate crisis. And more generally, we're interested in improving the quality, comfort, dignity, and cost of construction around the world. We focus in a range of applications. So we have people who focus in building structures and construction, people focused in building energy, occupant comfort, daylighting, et cetera. So we're a very unique program because we bring many different facets of building science and building technology together in one room. And we're a very collaborative and collegial community. So this is just an example from our welcome reception that we had at the beginning of the year a few years ago at the MIT Sailing Pavilion. This is another example of a hike that we went on a few years ago in New Hampshire. The BT community includes graduate students from 3 degree programs in the Department of Architecture that presumably you're here to learn more about today. We have the PhD program in building technology. And this is for advanced graduate students who already have research experience and are interested in a detailed research degree under the advisement of one of us, one of the faculty, focused in an area of building technology or building science. And then we also have 2 master's programs, the Master of Science in Building Technology, or it's also called SMBT. And this is intended as a research-oriented master's program for students who are coming from more of an engineering background, who also conduct 2-year-long deep research projects collaboratively with faculty advisors. And then we also have a 2-year master's program called the Master of Science in Architectural Studies. Here at MIT, we also call this SMARCS. The SMARCS BT is also a 2-year research program working closely on a thesis project under faculty advisement and is intended for students who have a more architectural background. So an undergraduate degree in architecture, potentially practice experience in architecture. It's a post-professional degree program. And so all of these students from all different backgrounds come together to form the BT community together with the faculty and staff. And with a serious place, we're really urgently interested in our research addressing the climate crisis and the built environment. But as I said, it's also a very friendly and collegial place where we enjoy getting together and collaborating. This is us this year at our welcome reception in September at a local restaurant. As I said, our mission is to help the building sector decarbonize and address inequality while working towards these urgent goals to get to net zero carbon emissions in buildings by 2050. As I said, we work across a range of technologies, areas of disciplinary expertise, and methodologies to develop design concepts, operational strategies, construction techniques that create buildings that support this mission. We're really eager to find new graduate students every year who share these interests and passions. And so we definitely encourage you to apply to one of our graduate programs if you share this interest. We know that the climate crisis is urgent. We know that we have a limited time to cap our global greenhouse gas emissions and temperature rises to 2 degrees Celsius. We have a carbon budget that must get to net zero, and a building stock in particular that must get to net zero by 2050. Our goal is to attack this from multiple angles. We focus on operational carbon, we focus on embodied carbon. We want to do all of this while also maintaining an equitable and innovative built environment. We aim to attract people like you, passionate individuals who have strong technical backgrounds and training to grow you into leaders in practice, in academia, and in research. Our program strives to fully fund, so tuition and stipend, all of the graduate students who enter our program. And that is from a kind of a mix of funding sources, from fellowship support to teaching assistantships to research assistantships on sponsored research projects. And we'll hear more about those possible sources of funding when we hear from individual faculty members. I'll stop sharing here. Before I go on, I'm going to talk a little bit about my own research, but I wonder, are there any basic questions about our 3 degree programs from anyone here? So we have the PhD, the Master of Science in Building Technology, and the SMARCS Building Technology degree. This is a common question. You can only apply to one of them, so we highly recommend tailoring your application to the program that you think best suits your background. If you have substantial research experience, and often that's measured through a peer-reviewed publication or more than one, the PhD could be the best program for you. If you're new to research, but you have a background in the fundamental building physics or building science that you're interested in, again, the SMBT is probably the right choice. And if you're in that same situation, but have an architectural design background, the SMARCS degree is most appropriate. Hopefully that's clear for everybody. No other questions yet? Wonderful. Well, I will start then by giving a brief overview of my own research interest, and then we'll hear from the other BT faculty who are currently here and who will join us shortly. Les Norford, Leon Glicksman, John Oxendorf, and Christoph Reinhardt, who are my colleagues. So let me start with an overview of my own research.
And maybe I'll just add, feel free to put questions in the chat also, or we'll have time for Q&A at the end as well.
Yeah, absolutely. All right, so I'll take off my BT director hat and I'll tell you a little bit more about my research. So I've been a member of the BT faculty since 2014, and since then I've established the Digital Structures Research Group, who come from a range of backgrounds between structural engineering, architectural design, and computing. And our major goal is to support the design and construction of structures that are highly responsive to our environmental and economical obligations to build low carbon, affordable construction at scale, to work with resources that are available, increasingly through questions of circularity and making use of underutilized or undervalued materials. We're also interested methodologically in supporting and creating design processes that integrate human expertise and interest and intent into computational workflows. And then we're also interested in creating and engaging with emerging construction processes, especially in digital fabrication. Our work focuses on advancing these emerging technologies across these motivations in design and construction to promote a more sustainable and equitable built environment. And broadly, our work falls into 2 categories. On the left, we work in fundamental methods in computation to support performance-driven design. A lot of that is linked to understanding early stage performance or understanding performance in early stage design to support creative design processes that are nevertheless resulting in very high performing outcomes. Increasingly, we're doing that by harnessing advances in machine learning. We're also very interested in scaling circular design through algorithmic methods. We do quite a lot of work in algorithmic circular design with a system we call digital circularity. I'll speak a little bit about that today. We're interested in general in integrating design processes across different building physics. Inputs from structural systems to thermal behavior, for example, and interested in designing for flexibility and longevity. In general, we engage with fabrication across a range of areas as well, including designing systems around available materials, as I mentioned, working with an understanding of supply chains, tooling techniques, and sort of available construction methods, and thinking about sort of designing circular systems that can be used and reused many times. I'll give a few examples of our work broadly, so you have a sense of the types of projects that we work on. This is an early tool that we developed at the beginning of my research, where I was really interested in new design tools that blended architectural design and structural performance. So this is a tool that allows designers to ideate through the creation of design alternatives, to understand performance here as a quantitative score that represents structural material requirements, how much material is required to support a load in this truss. And then this tool supports an interactive mode of engagement with the human designer who's able to give feedback to this algorithmic tool to generate new solutions that simultaneously balance the interests and needs and aesthetic preferences of the designer with quantitative measures of performance and material efficiency. With techniques like this, we can generate a wide range of interesting solutions. And so our research is often motivated by these dual goals of efficiency and diversity. So we're not necessarily looking only to optimize or find the very best solutions to a problem, because it's impossible to define that problem precisely mathematically. We're interested in tools that help designers come up with better solutions than they could come up with themselves, but also make use of their expertise and judgment and intent. Lately, we've been exploring kind of similar approaches on more complex problems, harnessing advances in data science and machine learning. So for example, a complex roof structure like this is very hard to explore by hand. There's billions and billions of possible iterations of different geometries that have different types of performance indications. By using a machine learning model called a variational autoencoder, we can compress this really large design space, this enormous amount of data, into a two-dimensional latent space that can then be again explored by a human. Here, the idea is this latent space contains a continuous landscape of design alternatives that are all high performing, that could potentially be explored as a new map or a new design space with interesting and new and surprising alternatives in structural design. We're also interested in engaging with this through new forms of interface between humans and computers. Here we have a project where we used sketches as a way to enter a design space. These sketches are then evaluated automatically using a surrogate model that we trained with synthetic training data. And then these sketches can be interpolated to produce new designs with performance information in them. So we're very interested in linking generative design and human-driven processes with instantaneous performance information. We're also interested in that connecting similar ideas of efficiency, carbon reduction, and geometry to very practical problems that can have immediate impact around the world. We've done a lot of work in reinforced concrete construction because it's one of the most prevalent forms of construction globally. It's what most housing around the world is made out of, and it's an extremely wasteful material process as it's often used now. We've done a lot of research on how we can substantially decarbonize concrete construction through geometry and efficiency-driven techniques. Here, we've built our own constrained optimization tool that removes unnecessary structural material from a one-way reinforced concrete floor system while still meeting today's building codes and using today's materials, finding new geometries and shapes that can orient forces in a more efficient way while saving substantial amounts of material. And in this work, we're very focused on impact. So we do large-scale construction and testing and working directly with partners in local organizations to demonstrate these techniques. We're also interested in more speculative fabrication techniques where addressing this question of complexity as structures become more efficient, require less carbon, let's say, to support a given load, they also become more complicated. Every node in this truss becomes different. Every bar has a different length as this truss morphs from a standardized design to an optimized design. So it would be impossible to build in a cost-effective way with today's construction techniques. But with emerging construction techniques like digital fabrication, here's an example of a 3D extrusion process with an end effector that we built mounted to a 6-axis robotic arm. The economics change dramatically. Every element has the same length here, but it would be just as easy for the robot to build a structure where every element is different. The logic to the robot is the same. And so generally across scales, it's the potential of digital fabrication to unlock materially efficient but complex designs is really exciting to us. These examples are small scale trusses, but we think the same kinds of application or the same kinds of ideas of using digital fabrication and CNC tooling can work across scales. This is an example that we did recently with partners in Mexico, working on a prototype for affordable housing construction. Here we combined our interest in shape-optimized reinforced concrete beams with robotically extruded precise material allocation to create a modification of a very classical construction system, the Vigueta y Bovedilla, or the block and beam system, that's shape-optimized to use about 50% less carbon than a typical system. The concrete beams have a varying shape along their length in response to their internal forces, and so the block that spans between them needs to be slightly different in every location. To address that, we worked with local partners who had a local ceramic material, a clay that they could extrude robotically, and we designed these individual blocks that were fired then in an electric kiln to structurally span between the individual concrete beams to create an interconnected floor system that is both the sort of aesthetic of the interior ceiling of the space, but also the structural system that uses a lot less material and a lot less cost than traditional structures. Finally, I'll speak a little bit about my work with circular materials. I got started thinking about circularity seriously about 6 years ago when I started working with tree forks, which I found to be a ubiquitous waste material around the world, and including in my neighborhood, where trees are taken down and chipped every day to make room for construction projects or because of invasive species. And typically when a tree is chipped, it becomes landscaping mulch, which rots in a few years, and all the carbon locked in the fibers is emitted back into the atmosphere. Instead, we noticed that these structural tree forks are really incredible moment transferring joints that in a tree act as cantilevers, have an incredible interior fiber structure that can transfer load much more efficiently than anything we can make by hand because of their three-dimensional nature, and that have really interesting geometries that could lend themselves to architectural form. So we developed a tool and a workflow to digitally inventory these tree forks and automatically allocate them to a target structure, which we could then modify to better match the geometries of the tree forks in our inventory. This is ongoing work that we've since developed into a really robust toolkit, and we've applied a very similar technique to a wide range of material systems, from salvaged dimensional lumber to concrete rubble, to bricks, to sawn timber. So it's a generalized approach. In this case, we used it with tree forks that we then digitally or use digital fabrication to process. We needed to remove the bark to improve their longevity and durability. So we used this robotic system where all the tool paths were automatically and algorithmically created, which resulted in a heterogeneous kit of parts where each little tree fork became a kind of custom Lego piece driven by its own internal geometry that then led to a really simple assembly process. Each piece was different, but it encoded exactly where it should be geometrically. So it was really simple to create a very complex structure, really driven by the characteristics of the inventory that we found. So I'm really excited about this kind of material-driven or inventory-driven design process, which flips the script on what really is the input into a design process, rather than imagining we have infinite material available to spend in designing and building anything we want. Now we can design in a way that's highly responsive to what's available. So with that, I'll stop and turn the floor over to one of my colleagues who will share their work next. I can't remember exactly who's next. Is it Les? Is it you? Or who's on deck?
Yeah, it is, but I'm seeing sharing is not turned on. You can request multiple presenter sharing for this meeting, send request, blah, blah, blah.
I just changed it. You can share now.
Okay. And okay, that should be good enough. Thank you, Caitlin, and greetings to all who joined us. I'm Les Norford. I have education in mechanical engineering and have been for some time largely interested in improving energy performance of buildings, but increasingly in recent years, realizing that involves consideration of structure. I've done some wonderful work with Caitlin, the electricity grid, and the urban environment in which buildings situate themselves. So a little bit about all of those. Much of the grid today, issues of grid are concerned batteries, energy storage. The sun shines at certain times of day, the wind blows and not at others. No one would design a battery made out of concrete. It has a thermal energy flow, but by any metric of energy storage or the rate at which power can be removed, a battery is kind of at the lower left of any graph or any metric one could come up with. And yet the energy storage in batteries is in masonry, in a masonry house, is equivalent to, say, if you adjust your thermostat up on your for cooling in the summer, it helps the grid, and over an hour in a given house, that can displace about 6 kilowatt hours of electrical cooling, or about half of the size of a Tesla Powerwall 2, and they're about $1,000 a kilowatt hour. So that sounds great. And for a long time, I thought, well, it's free because buildings have structures, and why not make use of the energy storage in them? We do that all the time. That thermal mass, so-called, will help buildings stay comfortable in a warmer day and also in a cooler night. For the grid, it not only means shifting loads away from peak periods where for generation, transmission, or distribution reasons, the grid can't meet those loads. And that'll increasingly be an issue as we decarbonize, as we electrify building energy uses like heating and cooling, but also at a shorter time scale where the sun is shining one minute and not the other, and utilities have to maintain voltage very carefully over second time intervals. And buildings can help with that, where air conditioning or heating systems can be adjusted at second intervals. And we don't feel that, again, because of the thermal storage in the structure of the building. But as Caitlin's work, John's work, and others indicates, there is a real cost to that material in terms of what we call embodied energy or embodied carbon. And Caitlin's work has shown that that can, to meet structural loads, horizontal elements, beams and slabs can shed about half of their mass and still meet those loads, reducing their embodied energy and carbon by that same percentage. So the question for me and students we've worked with has been, does that affect the thermal mass performance of the building? And largely the answer is well, shown there again a little left. It can be quantified in terms of how daytime highs can be squashed and nighttime lows can be increased. But if we look at different structures with different amounts of ribbing and so on, we can kind of assess the best possible trade-off of thermal performance with embodied energy or embodied carbon. And in which case the designer may want to choose something along that optimal frontier. But The net result of that is that in many cases, even losing half the mass, we come out a little better thermally. There's less material to hold thermal energy, but much of it deep in, say, a prismatic slab isn't used anyhow, and we have more surface area that promotes convective heat exchange. So the second piece of this is, okay, we're going to use thermal mass to store energy, but how do we eventually get rid of it? If we're storing up energy that keeps the building comfy in the day, but we've got to get rid of that at night somehow. Opening the windows is possibility, but there are better ways to consider that. One is shown in this diagram is to literally radiate it to the night through the atmosphere to outer space in wavelengths where the atmosphere is more or less transparent. And another would be to send it into the ground through kind of footings that Caitlin's team is optimizing, where the ground is cooler than the air in summer, warmer in winter, and therefore improves the kind of heat transfer you get with heat pumps. And these can work in ways where we assess this for different climates, where we're looking at losing energy to the sky and sort of the dark maroon, and to the ground and more of the orange. The total is in the gray. So in a place like Algiers, we can meet the full cooling load, even for fairly dense urban areas, with no active cooling. Cairo less so, and in a hot and heat climate, it's not appropriate. The density of the buildings matters in terms of and the size of the buildings, because it affects the footers and also how much of the sky you see. These same analyses can be used in extreme heat events. This is for Kuwait City, where the graph on the left shows that these are demands, and peak demand can be reduced most with that kind of magenta line, which is associated with pre-cooling, which means overcool a little bit in the morning and then cut back in the evening to help the grid. Better use of thermal mass also helps if you lose power, which is what the graph on the right is showing. So these are how slowly you can heat up to a level, how long it takes to heat up to a level where indoor conditions become potentially hazardous. And the index on the right is kind of the feels-like temperature that accounts for humidity. We're doing somewhat similar things on the MIT campus, looking at better accommodating thermal mass to tune buildings so that classrooms are heated when there are people in it and not otherwise, that offices are not heated and cooled over weekends. Things we would do in our own apartment or house if we're there to adjust the thermostat, but are harder in an automated system that involves hundreds of buildings and thousands of rooms. Some of this work involves what we would call a physics-based model, where heat storage is modeled as an electrical capacitor and heat resistance as an electrical resistor. So the same analytic machinery that our EE colleagues have developed over many years can be directly employed. These are also called some surrogate models. They represent the building physics with reasonable accuracy, and parameters can be fit from data with various mathematical techniques. And here again, we can get a trade-off between energy use and discomfort. If you're willing to have slightly cooler temperatures, how much energy can you save? And that can be with tuned models. We can plot this curve fairly precisely. And in addition to physics models, we're doing some machine learning. Primarily to account for interactions between groups of rooms in different parts of a building, and using the links in a graph convolutional neural net to represent those interactions, and then do the optimization with reinforcement learning. And then finally, the last one. Something different that came out of work that MIT had supported a number of us in BT to do in developing countries. This is looking at air quality problems associated with the burning of rice stubble in India's breadbasket, and the downwind transport of that into Delhi, the capital, which at this time of year is going through. It's a seasonal event. And so this was something of a transport and fluid mechanics problem that I worked on with people in Aero Astro. and to quantify the health impacts in lost and shortened lives, and encourage certain actions to avoid burning the stubble, but doing something else with it, including finding economically viable uses. The last piece of this was looking indoors. This is the Darby slum that was used in the movie, the site of the movie Slumdog Millionaire. 1 million people in a little over 2 square kilometers, hyperdense. The land is worth a fortune. Developers have been given permission to level some of it and do what they want, only if they provide adequate housing in less valuable land, shown on the right. And part of our work with colleagues there was to show that adequate really wasn't, not only was it physically unattractive, but the indoor air quality, which we got through various measurements, was worse. And then we publicized some of that and worked with governments there to share our results. So that's, I guess, indicating our interactivity and interactions with colleagues across the Institute. So Caitlin, back to you. Who's next in our hit parade?
Great. Our colleague Leon Glicksman is next.
Great. Thank you very much, Caitlin. And welcome to all of your visitors here in the Building Technology Program. This is a program we started 35 years ago. And again, the aim was really revolutionary, to combine traditional architectural studies with studies of people who are more interested in the technological side, engineering, design, and the like, related, as my colleagues have said, to energy efficiency in particular building structures, issues related to climate, indoor air quality, comfort, and the like. Also, as Caitlin said, and I think I should emphasize, unique part of our graduate program is from day one, you will be involved in original research project with a research advisor. A lot of the graduate students wonder about, well, as undergraduate, I'll take 4 or 5 subjects at one time. Here, what we say is you'll possibly at best take 2 or 3 subjects while you're doing the original research project. This is really a challenge for some of you who haven't done this before, but I think everyone who has done it has found it very rewarding, in the fact that you really are contributing to our knowledge and our engineering designs related to a number of issues within the environment. Again, we have students in our group who have architectural backgrounds. We have students from mechanical, electrical, sometimes civil engineering who are working with us. In fact, some of those students are actually getting degrees in those departments. So you'll get a wide breadth of learning by dealing with all of those particular students. And again, as Caitlin said, we try to provide funding, in fact, indeed provide funding to all of our students. This is tuition plus a stipend for your living costs. We do that, obviously, to make this a reasonable graduate experience for you. But the same token, we limit the number of graduate students we have in the program, so each student really has time to individually work one-on-one with a faculty advisor in the particular program. As our colleagues have said, a lot of our focus is on energy efficiency and the like. And I've done research in a number of different areas. And as some famous architects have said, less is more. So I'm just going to show you a couple of projects where we have particularly done things, if in fact I can find it here in my all right, so these are examples of several research projects we have undergrads. One is a project we're doing in Gujarat, India. It turns out that when people look at future energy needs of the world, one of the major needs is going to be for cooling requirements in places of South Asia and Africa and the like. These are areas in many cases where people have not had the luxury of air conditioning. And in fact, if everyone could afford air conditioning, the amount of energy that these would consume would overwhelm us in the near future, and really make it very difficult for us to meet some of the requirements for and the climate limitations. So some of the work we've done is working directly with people in India. In fact, we have a project in Gujarat, India right now underway to find ways that we can use natural ventilation plus thermal mass. Les Norford has told you about some of those in his project. And again, the idea is in the hottest part of the year, at night, the temperatures are fairly moderate. So what we'd like to do is bring a large amount of air into the building at night, cool the internal thermal mass, and then in the daytime, use that thermal mass to moderate the temperature peaks which occur during the middle of the day. And in some of the projects we've done already, we find we can reduce those temperature peaks. So if the indoor temperature is 5, in some cases 6 or 7 degrees C, lower than the peak outdoor temperatures. It may not be totally comfortable, but certainly it allows people to be safe and, in fact, be productive in their areas there. Another project where we've done a considerable amount of work is a natural ventilation in other buildings. This is a office building we worked on in Tokyo. We worked directly with the designers and engineers on this building. And again, the idea is, in this case, to use buoyancy-driven natural ventilation. The fact that the air temperature inside the building is considerably higher than outside, we get a chimney effect, and we get actually air circulating from the exterior envelope here, which is open, through a chimney effect to the roof. And again, can provide natural ventilation. In a climate like this, if we want to really achieve true comfort conditions, this system does not work year-round, but probably can meet about 50% of the cooling needs that would traditionally be used with air conditioning. And again, a part of, I think, that our students really enjoy is the learning process, being actually on site, working with these people. So it's more than just a theoretical study on computers, but it's actually working with these people and making sure that these technologies work properly. We've done some work in the past, particularly during the pandemic, to see what we can do to understand the dispersion of COVID. It turns out that a lot of the transfer of the COVID aerosols is simply by circulation with the air. The aerosol particles are so small, they actually just move with the movement of the air. So here is a project we're trying to understand just what is the air circulation patterns? What does it look like? What can we do to reduce the danger to people within the space? And found the typical 6-foot separation distance in some cases not adequate, that in fact we need to have a more subtle understanding of what goes on in this case. So this is actually a study we did of an existing MIT classroom to see what the effect is. If this individual here had COVID and was exhaling to these aerosol particles, where would they go? And one of the interesting things we found out is when an older MIT building, single glazed in the wintertime, where the window is very cold, the warm COVID particles initially rise, but some of them interact with the window and get cold and actually drop. So in fact, some of the COVIDs recirculated back into this area, and neighboring students have danger of being enveloped by those particular particles. So again, it's an idea of how do we redesign the circulation HVAC system to try and meet those problems. And then interestingly, this is something that we had done a lot of work on air circulation, and our colleagues in what's called the D Lab at MIT, who look on problems related to the developing world, we're looking at ways to essentially solve a problem of food spoilage. It turns out in very warm climates, once the fruits or vegetables are harvested, if they are not cooled rapidly within a day or two, if they're kept in very warm surroundings, the food deteriorates. In some cases in Africa and in Asia, our colleagues have found that as much as 50% of the food that's harvested is spoiled because of this heating effect of this. So what we've done is to try to develop an innovative concept where we put the cartons which contain the food into a old shipping container. We bring in hot air. We through fans and put it through a evaporative cooling system, and then force it through these the pallets which are containing the food, so we can rapidly cool the food. The advantage first is the food is cooled, so in fact it very quickly cools down and does not spoil. It turns out this system is very inexpensive to build and also very expensive to run. An alternative people have looked at is typical air conditioning refrigeration systems. They're far too costly in the developing world, and the amount of energy requirement is much too high. Presently, we have two projects going on, one in Gujarat, India, looking at this kind of technology, another one in Nigeria. And again, the people there are very enthused about the advantage of this, the low cost, easy to implement. All technologies do not have to be super sophisticated, easy to implement, and in fact, might make a major impact on the food security issue. So these are just examples of kinds of projects we've done which involve fairly detailed technical understanding, but again, really in the field, having the students interact with these people and help develop these projects. I hope these may be some things that you might be interested in.
Thanks so much, Leon. And now we're going to hear from John Oxendorf.
Hi, everyone. Welcome. It's great to have you here and to learn more about the BT program at MIT. I would like to share a little bit about the research that my students and I have done together, but I also want to give a bit of an overview of the department and where we're going in the next couple of years. This is an image of a adaptive reuse project, which is on the MIT campus, a 130-year-old brick warehouse that will be the future home of architecture and urban planning at MIT. And it's due to open in about 2 years and in 26. And it also includes a new design initiative across all of MIT, elevating collaborative design approaches to challenging problems that I'm directing. And so I give that as a little bit of a general background that if you end up coming to MIT for grad school, there's a reasonable chance you'll be in this new building with us in about 2 years. It's a pretty exciting project under construction right now. Architects are Diller, Scofidio, Renfro. And but just a little bit about the work of my students and I over many years. I always like to start with this staircase. This is a thin tile brick vaulted staircase on the campus of Carnegie Mellon, built by Rafael Guastavino Jr., who stopped formal education at age 10, and this staircase would not be possible under almost any building code in the world. And yet it's been working very well in Pittsburgh for more than a century. And in fact, it's in the civil engineering building at Carnegie Mellon. So generations of students go up and down this stair, but it doesn't have any steel in it. It's made of brittle steel, brittle ceramic tile. It's completed in 1914, and I like to point out the same year Corbusier proposes this staircase, which is very complicated to build, requires a lot of rebar, wasn't built at the time. But for me, it's an example of how in the built environment, we often fall prey to progress ideology that all around the world, we've continued to imagine this is really the best possible way to build stairs. And we learn from history a lot in my group. So this is an example of this method of thin tile vaults. It's an Islamic construction technique more than a century old. The bricks are placed with a fast setting mortar. And if you get the geometry right, this is 1 brick thick. It has high load capacity through the double curvature. So this is an unreinforced brick shell. And when Les and Leon took a chance on hiring me almost 25 years ago now, and I'll always be grateful to them, I had been inspired by this masonry vault in England and others trying to understand how stones could be stable purely through their geometry with no tensile connections in them. And yet today we often, as engineers, and I'm trained as a structural engineer, are asked to make designs stand up that are not great designs. This is one I visited many times, couldn't understand how it stood up, and then of course learned one day it didn't. This is the Charles de Gaulle airport collapse, which was a real tragedy, and we could talk much more about it, but it's an example of a broken design process and a wasteful design process, especially in light of the climate crisis. So over the last 20 years or more at MIT, we've been pioneering new design techniques in particular, and resuscitating old ones like graphic statics as a means of discovering geometrical form, and using that for design projects like this Mapungubwe Interpretive Center in South Africa, made of local brick, and using primarily local labor, or similarly the drone port at the Venice Biennale that we did in collaboration with Norman Foster Foundation at the 2016 Biennale, together with two MIT graduates, Luisel and Sixto at the time. And I show you these vaulted low carbon projects like the Mapungubwe Center in South Africa that are using about 60 kilograms of CO2 per square meter. That's about 12 pounds per square foot of CO2 equivalent or global warming potential. The London Olympic Stadium is about 4 times that in terms of carbon intensity, and then the Bird's Nest in Beijing per square meter is another 5 times London. So from a carbon intensity, and this is embodied carbon only, this is not operational carbon, the Bird's Nest is incredibly wasteful. The London Olympic Stadium is kind of best practice with conventional steel and concrete, and Mapungubwe is thinking in a totally different way about using local materials and minimizing steel and cement. We also showcased this idea at the Venice Biennale in 2016, and Nebu Hale, a current PhD student, has been developing low carbon unreinforced vaulted floor systems, and we'll be building prototypes in Ethiopia next year. And so this is a really active area of work for us, as Caitlin was pointing out, because concrete construction, especially in emerging markets, is both expensive and environmentally and harmful. What Nebu is trying to do is to really win in the marketplace. If you can develop floor systems that are less than half the price of conventional concrete slabs in Addis Ababa, for example, by reducing the imported steel and cement, then you can win in the marketplace, and then the lower carbon is a bonus. These are about half the carbon and about half the cost of conventional concrete slabs. We also collaborated with the Block Research Group at ETH for the same Biennale with various ribbed floor systems that they've been developing further, and more of a showcase project with 400 pieces of thin Texas limestone held in place only by compression with no mortar and no pins. So this is the Armadillo Vault, developed largely by BRG, but I helped with the conceptual design as well as with the engineering of it. And then a project that I really helped lead on campus is the Collier Memorial, made of granite stones, together with architects Howler and Yoon. If you're in Cambridge, please come visit that. And if you end up at MIT, you won't be able to escape visiting it with me at some point, because it was a really meaningful project, and I always like to share the work we did there. And then another built work on campus, a student, Joe Damon, almost 20 years ago, developed this rammed earth wall on the MIT campus, which doesn't have cement. It's just clay, sand, and gravel. And we've done a long-term weathering study that we just published of how the wall is weathered in the New England climate. And another current student I'd like to highlight is Juliana Berglund Brown, who for her PhD is working on reused steel elements, like you see at the bottom of this image. And Juliana and I have just received an EPA grant to develop EPDs, environmental product declarations, for reused steel in projects. And that's a 3-year project that will be kicking off in 25. So if you're interested in reuse, this is another case like Nebu's floor systems, where this has lower cost and lower carbon. And we think anywhere in the built environment, we can find solutions that save money and save carbon. They're no-brainers, and we should try to help develop them and promote them. So, in summary, if we look at the work of my group, you can find it across these books or within journal papers, but we think the history of construction is fertile ground for designers. We can discover new forms with the structural imperative, and we are obviously close allies with the work that Digital Structures group does with Professor Caitlin Mueller. But my group tends to differentiate itself in some ways, and one of the things we do is really try to look at traditional materials and systems like these vaulted earth and clay systems, as well as form finding. And maybe one last thing I would end with is that we produce a lot of papers out of the building technology group, and we're known for our research, but what we really pride ourselves in are the people who come out of our group and where they go and what they do. And so I'm very proud of all these alums of our group and all the things that they're doing out in the world now. So with that, thank you so much, and I'd be happy to answer any questions, and I'll hand it back to Caitlin as our guru.
That was wonderful. Yes, we'll have a little bit of time for questions in a few minutes. I just want to turn the floor over to our final colleague who's very graciously joining us from the middle of a workshop he's running at the Harvard Law School, Christoph Reinhardt. Christoph, if you'd like to speak for a few minutes, we'd love to hear from you.
Sure, yeah, thank you. First of all, welcome to all of you. Thanks a lot for the interest in the Building Technology program. You already heard from my wonderful colleagues about all the exciting work that they're doing, and I'll just add a little bit to that as well. And I keep it at just a couple of minutes. These are quickly thrown together slides, but hopefully they capture some of the ongoing work. So within building technology, as you probably already heard, we do a lot of collaborative work among the faculty, but we also work with students one-on-one very closely. And these groups or labs, as we call them, have basically developed deep areas of expertise in different complementary settings. So I've been working with a group that's called the Sustainable Design Lab. Roughly speaking, we are developing design workflows, planning tools, metrics for education and practice to evaluate the environmental performance of buildings and neighborhoods. So how do we, during the design process or during building operation, come up with better ways on how to design buildings that are more energy efficient, have higher thermal comfort, better quality, that are affordable. And in recent years, as you will see in a bit, we expanded our work from the individual buildings to also look at cities, neighborhoods. And I would say right now we want to tackle really every building in the world. So part of this, our research is looking at teaching evidence-based design. And I think this echoes what you heard from my colleagues, that it's really important for us that we are in a school of architecture. That's not by accident. And we really want to teach the fundamentals of building science in a way that is actionable for designers and architects. So when it comes to something really foundational, such as solar radiation, then we try to first explain, well, when you're anywhere on Earth, where is actually the sun, and how can you really reliably predict where the sun is located? But then very quickly getting into questions, how can I use this to create good shading situations for outer urban spaces, for indoor situations? How can I convert the same theory into predictions of where we have good solar photovoltaics and so forth? And in order to generate this arch between fundamental science and how is this actionable for designers, we've been working on a simulation environment called Climate Studio that we're using for teaching here. It's used now in over 700 schools of architecture, taught by to about 20,000 students per year. And we are working closely with these various architecture firms that you see here, where we are meeting once a month to talk about different ways of how can we actually display building performance related information during the design process to a designer, and how can we make that actionable. And to give you a little bit of sense of how we teach the subject matter, this is a simulation game that we play in the architecture VT1 class instead of a midterm every year. Here you see the students. I know this looks like a Dunkin' Donut commercial, but actually the students are are basically using a computer program custom made for this class where they have 90 minutes to design the most energy efficient in time and on budget. So we're trying really to bring it all together. How can you design quickly and efficiently? And this all gets then translated into websites where we try to make this information available to an audience within MIT and beyond. So we have here this 8 steps toward net zero building design. So this covers really the role of education. What our group is currently really engaged in is this MIT climate project that you might have heard of. It's an MIT-wide, we call it a whole of MIT initiative, where we try to bring all of the activities within MIT and in the world to look at the big questions related to combating climate change. And so we have different missions there. One mission that we are particularly involved in is the Building and Adapting Healthy and Resilient Cities mission. And a lot of the ongoing work within the lab will be in support of this mission in the coming years. And so one particular area is this urban analytics field, where this is an old example where you are seeing a solar radiation analysis of the MIT campus. We created a web app that basically provides information very detailed on solar rooftop potential to owners. Right now, the map covers actually nearly 100 million US homes. And you can basically see as an owner whether it's worthwhile for you to put a PV system on your rooftop or not. And we've done various case studies that shown that this leads to a lot of action. So we have very high rates of owners adopting a solar system. And right now, what we're doing is we're going from the rooftop of the building into the building. This is something we've developed the basic fundamentals for a whole year. So we're bringing here various areas together, GIS data set, other large urban data sets. We are combining that with climate data, with energy models, so that we are able to predict building by building energy use for every building. Initially, we did this type of work in cities. So in 2016, that was we call it an Uber model of the city of Boston, where we worked with the Massachusetts Clean Energy Center and Lincoln Laboratory on modeling 80,000 buildings in Boston and understand how different energy district systems could be deployed within the city. Since then, this activity has moved more towards, I would say, even energy policy levels. How can city governments and countries reduce carbon emissions of the building sector on a large scale? So a typical application would be a city knows how much carbon they use. They know by how much they want to reduce it. Typically, everybody wants to become net zero by 2050. Doesn't really know how they can get there, but this is a political goal. So we help to translate this. So this is a case study for Oshkosh, Wisconsin. And there where we basically showed them this technology pathway that we developed with them initially, carbon emissions for the whole city, how much natural gas and electricity do you use? And if you use a different combination of efficiency measures, how do you actually reach your target? And the cities find that useful and empowering because they can use that to rally their troops, so to speak, the residents, that they know what they have to do to meet these targets. The goal has then been to implement these methods anywhere on Earth. So we've done case study in these 25 cities that you see here, and we've made more and more progress understanding who the relevant actors are. So in this phase of the project, we had sustainability champions for each city, GIS managers, and energy modelers, which is like a bread and butter knowledge and technology within building technology. And in order to go from 25 cities to ideally every city in the world, we are working on this global building inventory right now. This involves a whole bunch of groups within MIT, where we're looking at current and future weather data, building massings for anywhere in the world, building descriptions. We are combining that with various modeling engines. I use building energy modeling here. Caitlin and I talked about expanding this to embodied energy use as well. And then we end up with a global map of every building in cities, if not anywhere. And then we can put filtering on top of that. We plan to make this available for free downloads for everybody, so that we basically provide the power to all different stakeholders that might be interested in that. So we can say these are the buildings that are very likely to have excessive energy usage or a high heat risk. So there are a whole bunch of different case studies that can be applied here. And just to give you a first sense, this is something that one PhD student in the lab put together, Sam Balk. This is an energy model. This is a model of 2.5 million buildings in Massachusetts. So we basically have a building model for each of these buildings. You can basically zoom in and for each building say what is the likelihood of, say, how much energy you're going to save, how this is going to change your energy bill if you are implementing a heat pump, for example. And there the big message is, depending on what your fuel use is, if you have natural gas, which is very cheap, or do you have oil, then the economics are very different. And it's important for policymakers to understand this and basically formulate policies accordingly. So I'm going to jump in the interest of time. Yeah, this was, as Caitlin just said, I just came from a seminar at Harvard Law School where we asked this question to the becoming attorneys: is cooling a human right? We looked at a case study in India and tried to understand what does this actually mean, that air conditioning is a human right? Is this enforceable? Who are the plaintiffs? Who are the defendants in a case like this? And I think this type of interaction that we seek within building technology, that we go beyond our own area of expertise and work with others, that is really one of the aspects of this community. That's probably my favorite, after all. So just in closing, thank you so much for your interest in our program and in building science in general. We have only a few thousand building scientists in the world, and there are so many buildings, and there's so much help that these buildings need. So climate change is happening now. We are running out of time, and we deeply hope that you will pursue a career in this field with us or with others. And of course, if you have any questions, please feel free to contact me. Thank you.
Thank you so much, Christoph. So we only have a few minutes live for questions with the faculty. And so I would say if you have very specific questions, you could either put them into the chat or write to faculty individually. But I'll try to prioritize questions that have the broadest applicability to all of you. So Will, thank you very much for giving your question here. What constitutes a sufficient technical background for admission to the SMBT program? Typically, we expect some kind of science or engineering degree for your undergraduate or a previous degree. Usually that means familiarity with advanced mathematics. A lot of our work involves things like linear algebra or differential equations, or it might mean familiarity with computer programming or some of the scientific and physical fundamentals of heat transfer or building energy modeling or structural mechanics. So we would expect that you have some expertise in one of those fields through academic work. Is there a track record of students in the MArch program at MIT entering the SMBT later in their studies? And what does the preparation look like? It's not common for students to go from the MArch to the SMBT, but we have had examples where that has happened. With a kind of confluence of funding opportunities and mutual interests between students and faculty. The MArch program is quite different from our building technology focused research programs because it's a professional program emphasizing sort of breadth across the discipline. All of us are also very involved with the MArch program. We love the MArch program. We teach in the MArch program. We advise students in that program. So that's another way to get involved with building technology. The distinction is really this like intense research experience, working very closely with a faculty advisor. In examples where people have gone from the MArch to the SMBT, the opportunities have emerged for that to happen, mostly because of a strong research focus and interest. Okay, great question about statement of objectives. Yes, so this is true not just for the SMBT program, but all three of our degree programs require a statement. And we have fairly specific expectations for this that I'm very happy to elaborate on right now. The prompt in the admissions portal is accurate. So it asks you to speak to your specific interests, your background and preparation, and what you'd like to do at MIT and with whom, with which faculty members. So all of that information is very important. The statement should include both a detailed overview of your professional background and how that has informed your research interests and priorities and areas of expertise. And then it should also include statements about your prospective research agenda. What research questions are especially interesting to you? What methodologies would you like to employ? With what faculty members would you like to pursue this research? The more direct you can be, the better. The more you can really demonstrate expertise in the background, your understanding of the literature and context in the field, that is all really helpful information for us. The project or area of interest that you describe in your statement is not necessarily exactly what you will work on if you're admitted to our program, and yet it is very helpful for us to understand how you see the world, what you are most passionate about, what problems really drive you. The statement ideally is something like 2 pages, no more than 3, and it should really be quite focused. Great. Any other questions? Oh, so Alia, you're interested in sustainable passive design, the SMARCS in BT. Yeah, I mean, both of these are possible, Alia. So you're interested in whether you should do a SMARCS in BT or an AD architectural design. Either could work. The big difference is really in BT, the thesis project is very clearly connected to one of the faculty's research agendas. If you want to describe your project in a way that it could take place, let's say in the Sustainable Design Lab or with another faculty member, that would be a really good fit. If you'd like to pursue a more independent project, the Architectural Design SMARCS might be more appropriate for you because that program is less closely linked to faculty research. I'm sorry, other faculty, please feel free to jump in for some of these questions. I don't mean to take all of them.
Yeah,
go ahead,
I had
please.
added only for Alia that the faculty members you might want to work with matters, and for everyone, there's a website that has prior theses, which is DSpace at MIT. I'll put the link in the chat. And that's a good way of seeing what kinds of projects students do with which faculty members as advisor, and you could see which one better aligns with you. But I agree with Caitlin, both AD and BT could be appropriate for you.
Gideon, for your question about autonomous construction, it is a topic that we cover in BT, both me and potentially some new faculty members who will be joining in the future. So I think you could definitely apply in BT for that topic. The Design and Computation SMARCS program also has a focus on digital fabrication and autonomous construction. I know you have to just choose one, so I would decide which of the 2 programs you want to apply for. Either one could be appropriate. And I suggest also looking at the computation program. Industry partners, yes, there's a lot of engagement with industry in our program and at MIT, partly through funding. Many of us have projects funded through industry collaborations or through MIT-wide initiatives that connect industry sponsors to academic research. For example, I'm the associate director of the MIT Climate and Sustainability Consortium, which is an industry-focused research program. Christoph is also very involved with a lot of industry outreach. Many of us are. So that can take a lot of different, that can mean working closely with a collaborator who's based in industry in, let's say, like sustainability or decarbonization sector. It could mean doing an internship somewhere where you're working on deploying some of the ideas you've developed in your research in a, let's say, design practice or an engineering context. We're very interested in that. We're all here to make an impact in the world, and we know that industry is a major way to do that. So we're very open to that.
And maybe just to add to that, the way that usually works, if we find applicants suitable and we see a certain fit, very often we might at one point reach out and discuss this. So you won't be accepted to the program and then be expected to work with a certain industry group if you don't know about it. So this is very transparent beforehand.
Great. And so your question about a PhD in architecture, you don't need to contact us before applying. And maybe this is the last thing I'll say before we turn off the recording and turn it over to the existing graduate students. As Christoph said, we're really enthusiastic about the area that we work in, and we're very excited for you to join in this area, whether it's with us or in general. Many of us get thousands of emails a day, so if you try to reach out to us and you don't hear back, don't take that as a negative sign. It may just be that it is impossible for us to respond. By far, the best way to be considered for the program is to apply. So even if you don't hear back from us, if you have a strong interest and you can look at our websites or Google Scholar and figure out sort of the areas that we work in, strongly recommend you do that and apply. We will try to respond to you individually, but our schedules don't always allow us to do that. And I wouldn't take that personally or as a negative sign. That's partly why we're having this event, is to communicate with you as clearly as we can in a equitable way. So apologies in advance if we're not able to respond to every individual query, but highly encourage you to apply. That's the best way for us to see your information. Great. Well, with that, we will, Georgia, if you don't mind, stop recording. And I think are Daria and Ben and Rachel